Okay, so we are back. Problem number 43. U-substitution would probably be a good idea here because I could already see that when I take the derivative of 2y to the fourth minus 1, that's going to feature a y to the third in that derivative, and that's probably going to be something that can cancel with this y to the third. So let's go ahead and try U-substitution, and we're going to say that u is equal to 2y to the fourth minus 1. Therefore, du is clearly going to be 8y to the third dy. And then we can solve for dy. That would become du over 8y to the third. And therefore, this is a substitution opportunity. And that's a substitution opportunity, the yellow boxes. So anytime we see a 2y to the fourth minus 1, it could be replaced with a u. Anytime we see a dy, it could be replaced with this. We're going to try it. We have the y to the third, once again, minding its own business. We have the square root of u, and instead of dy, we have du over 8y to the third. There is secretly a 1 above that 8, so really what's been introduced is a 1/8. I think we would all agree that the y to the thirds would cancel, and what we are therefore left with is the integral of the square root of u du. So that's something that's definitely workable. After actually performing the integration, it would become u to the 3/2, and it's really 2/3 plus c. Okay, the reason for that is because it's really u to the 1/2, and then when you apply the power rule, it's going to become this, u to the 3/2, and then multiplied times a new coefficient of 2 over 3. At that point, we are ready to substitute. So we're just kind of barreling through this one. I got to tell you, this one's pretty quick. We got this scenario here after substituting 2y to the fourth minus 1 in for u. Let's not forget that exponent, and then we have plus c, and then we are done. Okay, so this is kind of interesting. We have 1/2, 1/6, cosine of pi times t, cotangent of pi times t. Well, the good news is we already have this right here, so we know that the integral of cosine of cosecant x times cotangent x is equal to this. So this stands out as a strong possibility of something we could do. I also can kind of foresee that we will probably need the unit circle at some point. So we're going to just keep that there for now. Okay, so the u substitution would be u equals pi t. The derivative of that would just be pi dt. Therefore, dt equals du over pi, which really shouldn't be a problem. Let's see, I'll move this over. So when it comes to this, I think we would agree that what we really therefore have is cosecant u times cotangent u, and instead of writing dt, I'm going to write du over pi. And I think we would agree that that pi, sure, it's in the denominator, but there's also a 1 over it. So in reality, we could put that out here. I'm going to go ahead and do that now just to save time and room, and we're going to erase this. Okay. So I think we're ready to go ahead and perform this. It's going to be negative cosecant of u. So we're going to have 1 over pi on the outside. It's going to be negative cosecant of u. Instead of plus c, we have the 1/2 and the 1/6 to contend with. So we're going to put that up here. It's 1/2, 1/6. And let's work this out. I'm going to say let's keep the 1 over pi on the outside. And we're just going to do substitution here. It's clearly, what is it, pi times t. And really, this is what we're dealing with, right? And If we were to go further with it, it would be 1 over pi, negative cosecant pi times something minus negative cosecant pi times something. Okay, so kind of complicated. You do have to stay like relatively organized with regards to what those somethings are. We're going to have 1/2 and 1/6. 1/2 and 1/6. So my question therefore is, what is negative cosecant of pi over 2? Well, cosecant is the inverse operation of sine, and sine of pi over 2, if you look at the unit circle, sine of pi over 2 is 1. So it's not the inverse, rather, it's the reciprocal. So cosecant is the reciprocal of that. So the cosecant of pi over 2 is also going to be 1. So what we're really dealing with there is just a negative 1, actually. And then we're going to be subtracting whatever the yellow quantity is here. So now the question is, what's negative cosecant pi over 6? Well, sine of pi over 6 is 1/2. So the reciprocal of that is 2 over 1. So it's going to be negative 2 over 1, also known as negative 2. So that's the way to reason through that one. As a result of all of this, we have negative 1 plus 2, which is just 1, and therefore the answer would be 1 over pi. This one appears to be pretty tricky because if you just simply called u x minus 1 and then the derivative of that dx, that wouldn't help us with canceling out this x at all. Similarly, if you had u equals x, well then du would be dx again, and that would not help us with canceling out that radical there. So we do have a bit of a problem on our hands now. I think that this problem could be understood to be something of a special type of problem. Now, what I'm going to recommend is force this x on the outside. If you have an x times a radical x whatever like this, force this one to match this somehow. So for example, we can realize that x, well, x is really just x minus 1 plus 1. Okay, so just bear with me with this, and it's going to be that. Okay, so to maybe make it a little bit more clear, I'm actually going to write the original thing above and color code it somewhat. So the green x just became that. All right, the green became the green. And let's see, if that was a radical, then we'd be able to do some interesting things. So I'm not sure if this is just the way the teacher teaches it, but I think if we knew that this was a radical, then we could sort of distribute this other radical, x minus 1. Now, we're not allowed to just turn that into a radical without kind of simultaneously canceling that activity, okay? So hopefully you realize that radical x minus 1 squared is really just x minus 1. So in a way, we're building this up. And now we can distribute in a way that might be useful for us. So we would have, looks like it would be radical x minus 1 to the third plus radical x minus 1. All right, now this should really be a dx after all these. So hopefully that makes sense. I wonder if the moral of the story here is to just force a situation where you're only dealing with terms that feature radical x minus 1, and just kind of make that happen. Construct this out so that that can happen. Now, at that point, we should be able to set u equal to x minus 1, I believe. Yeah, because then the derivative of that would just be dx again, and therefore we can replace all the x minus 1s with a u. So this would become radical u to the third plus radical u, and it would be du because dx is equal to du. And I think a better way of writing that would be to say that this is u to the 3/2 plus u to the 1/2. And then we have du. Now we're ready. It would be u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 with the 2 and the 1. We could then substitute u in there, and u is right here. Anytime you see a u, it's really x minus 1. So that would become 2/5 x minus 1 raised to the 5/2 plus 2/3 x minus 1 raised to the 3/2, like that. At that point, I think we're ready to go ahead and substitute. It would be 2/5 times something minus 1 raised to the 5/2 plus 2/3 times something minus 1 raised to the 3/2, and that would be subtracting the entire quantity of 2/5 times something minus 1 again raised to the 5/2 plus 2/3 times something minus 1 raised to the 3/2. And that will end up being the answer after plugging in 2 and 1. So the first number is 2. The next number is 1. 2 minus 1 is just 1. 1 raised to the 5/2 is just 1. So that's going to be 2/5. 2 minus 1 is just 1. So it's going to be 2/5 plus 2/3. Already we can see that. We are then going to be subtracting the red brackets. So the red brackets say 1 minus 1 is 0. 1 minus 1 is 0. So this whole thing is going to be a 0. And therefore, we are looking at 6/15 plus 10/15. And that would be 16/15. So that was quite a journey. Yeah, quick review. If you see something where U-substitution isn't working and you have some x on the outside of a radical, construct this as follows. Make sure that you're preserving the value of x. Like, this is all still x, right? Because radical x minus 1 squared, well, that's just x minus 1, and x minus 1 plus 1 is just x, okay? So you got to make sure that you're constructing it in such a way that you actually do not change the value of x. Now, there might be a better way of doing that, but that's the only way that I would know how to do that at this point. All right, so anyway, 6/15 is the answer. Okay, so problem number 46 relies on your ability to remember these trigonometric, or these Pythagorean identities, I should say. Also, it requires a familiarity with this derivative as well, and some of these integrals. So it's actually, this one requires you to know a lot about a few things. So basically what you have to do is, I'm going to rewrite it in such a way that I do not write pi over 6 just to save time, but we're going to remember that step at the end. Truth is that that whole thing could be rewritten as this. And tan squared x could be rewritten as secant squared x minus 1. So I'm going to go ahead and do that. That is secant squared x minus 1 times tan x. Now, at that stage, we are able to set u equal to secant x, and then the derivative of that would become secant x tan x dx. And therefore, dx is equal to du over secant x tan x. So over here in red, the red integral, we would have, let's see, a scenario where u is secant. So we're going to replace that with u squared minus 1. We still have this tan here of x, and then instead of dx, we're going to write du over secant x tan x. Now, as a result of that, I think we could see the tans would cancel. The secant x that remains in the denominator here, well, in reality, that could be replaced by a u. In fact, I could have written that here, but we'll just replace this secant x with a u right now. So I'm going to go ahead and just write that now. And therefore, it can be acknowledged that there's really a 1 over u right here. We have a fraction called 1 over u. That blue fraction, not the du, we'll leave the du on the outside, but that 1 over u could be distributed in there into the parentheses. So as a result, that would become u minus ultimately 1 over u, and that would be du. Now the integral of 1 over u is ln absolute value of u plus c. Okay, so that's something to keep in mind when you're looking at this one. I say we go ahead and pull the trigger on the antiderivative, and let's now also just remind ourselves that we have these in the bounds. So when we perform the antiderivative, it's going to become u squared over 2 minus ln absolute value of u, and then we have pi over 6 and negative pi over 6. U was secant x, so we could simply write secant squared x over 2, or maybe we could even say 1/2 secant squared x minus ln of the absolute value of secant x, and that is going to be with these. And at that point, I am ready personally to begin the process of substitution. So it's going to be secant squared something minus ln absolute value of secant of something. And we're going to be subtracting an entire quantity of 1/2 secant squared something minus ln absolute value of secant something. And plugging in the values of pi over 6 and negative pi over 6, we'd have pi over 6, pi over 6, negative pi over 6, negative pi over 6. I think at this stage we could use the unit circle. So the secant of pi over 6, well, secant is the reciprocal of cosine. So the cosine of pi over 6 is radical 3 over 2. So the reciprocal of that is going to be 2 over radical 3, which becomes 2 radical 3 over 3. So that's the secant of pi over 6. It's 2 radical 3 over 3. So we're going to be multiplying 1/2 times that, 2 radical 3 over 3, but that's going to be squared, which we could worry about later. And it's going to be minus the natural log of the absolute value of 2 radical 3 over 3. And we will then be subtracting this stuff. So it's going to be 1/2. Now, the secant of negative pi over 6, well, negative pi over 6 is here, and that's actually going to be the same thing, believe it or not. Secant squared of negative pi over 6, well, that's going to be 2 radical 3 over 3 again, okay, because the cosine of pi over 6 is equal to the cosine of 11 pi over 6, so therefore the secant of pi over 6 is equal to the secant of 11 pi over 6. So what I'm seeing here is we're going to be subtracting the exact same thing. So the whole thing equals 0. We can save ourselves all that work by simply acknowledging that we're going to subtract some quantity minus the exact same quantity. So that's 0. So that's the answer. This one was tricky on multiple levels. Okay, on multiple levels it was tricky. But yeah, pause the video, look it over, try it yourself, see what happens. We were spared at the end from doing a lot of complicated stuff, so it's nice to see that it just turns out to be 0. So in my view, this is not calculus. This is literally just solving a system of equations, which is algebra. So I'm not really sure what's going on here, but the good news is I mean, it's not that hard, really. I mean, you got this fact based off of the first equation. Therefore, the second equation could be written thusly. Instead of x squared, we could now write y squared. We could solve for y at this point. And take it from there. I'm going to go ahead and divide everything by -1 right now. So it would be this. And factoring out a y would give us this. And I don't think there's anything tricky about these. Maybe, I don't know, in the comments below, if I'm missing something, just let me know. Yeah, y equals 0. And if we were to set y cubed minus 1 equal to 0, then y would be 1. So we could say, oh, okay, so there's 2 answers for what y is, and therefore when investigating what x is, well, we could use this actually. When y is 0, x would be 0, so we know that that's sort of one pair of solutions. And then when it comes to this, it would be x equals 1. And ultimately what this means is that these two graphs intersect each other at the points 0, 0 and 1, 1. So there you go. And problem 48 is similar. The first equation, we can certainly solve for y in terms of x at least by doing that. And the second equation, we could go ahead and just go through the motions, plugging in 24 over x here. So that's going to be 2x squared minus something over x squared. What is 24 squared? That is 576 plus 4 equals 0. At this point, I do not see any reason why we can't just multiply everything by x squared now, because we're going to want to knock out this denominator. And that is precisely what would happen. These would get canceled. This would become 2x to the fourth minus 576 plus 4x squared, and that's going to equal 0. At that point, I believe we could probably divide everything by 2. So we would have x to the fourth. I'm just going to rearrange it a little bit. It's going to be plus 2x squared minus 288, and that equals 0. At this point, we should be able to probably factor that. Now, anytime you have an even exponent here and the middle term exponent is half that, you could always just sort of factor it in a relatively normal way, only we want that to be x squared and that to be x squared. So that's a decent rule of thumb. And then with regards to these numbers here, we're essentially asking ourselves the same question we would ask under normal circumstances. And that question is, what two numbers multiply to negative 288 but add to positive 2? Now, 288, unfortunately, has a lot of factors, but it turns out that 16 times 18 gives you 288. One of them has to be positive, the other has to be negative. I think we can all agree this one needs to be positive and this one needs to be negative. So investigating further, we can see that when we decide to set this equal to 0, x would equal plus minus 4. When we decide to set this equal to 0, we'd end up in a situation that says x squared equals negative 18, and that is impossible because we don't want to be taking the square root of a negative number, so we could just discard that. So we know that, the x is going to be positive 4, and we have another x that's going to be negative 4. So the y that corresponds with this scenario could be found by going to this equation. 24 divided by 4 is 6, and then the y over here would be negative 6 because it's a negative 4. So that is how you do that one also. We can conclude that this point is a point of intersection and this point is a point of intersection. So that's how you do 48.